Hi there, it's Paul with a novel explanation of the meaning of divergence and curl. I should do this using multiple integrals, but since we won't be doing multiple integrals until the spring term, I've settled for a replacement involving averaging. I'm going to have to take some derivatives, so I load the numDeriv library, and now let me set up a vector field. A vector field requires two functions, one of which gives the first or x component of the field, the second of which gives the second or y component. But for taking derivatives in R, I also need to specify these in a form where I'm taking a function of a single vector and replace x by v sub 1, y by v sub 2. So let's plot this field. We plot it as anchored vectors. Leave plenty of space for our plot. Scale down the arrows that represent the field so they fit nicely on the screen, and then run through our pairs of points x and y and draw an arrow at each point, an anchored vector that shows the value of the vector field at that point. So there's your beautiful diagram. The vector shows the value of the vector field at each point on the diagram, and you look at it and say, well, it does seem to be sort of circling around in a counterclockwise way, and it appears to be moving generally outward away from the origin. Let's focus on the derivative of this now and see if we can quantify those ideas. We know how to do derivatives, of course. We just take the Jacobian matrix and we get a matrix with 4 entries. And this, of course, specifies a linear function, and it arguably specifies a vector field in the sense that given an increment, the vector h, it specifies the resulting change, namely df acting on h. So I will choose some rather small values for the components of the increment and do exactly the same sort of plot, drawing a bunch of arrows. And doesn't that look nice? It's nice and uniform, and when you look at it, you can say, well, it's clear. If I move outward away from the center of the diagram, the field points out also. It's also clear that the field is unambiguously circling around counterclockwise rather than clockwise. The first of these properties relates to the so-called divergence of the field, the second of them to its curl. Now let's see if we can come up with a number that measures divergence. If I pick a specific increment vector, for example, one whose first component is 1, whose second component is minus 1, let df act on h to get another vector, and then sum the products of the components to take the dot product. In that particular case, I get a value of 6, but I've chosen a very specific increment vector. In order to verify that the field on average points out, I need to average over vectors in all directions. In 2 dimensions, this is easily done. What I do is to generate a random angle, theta, between 0 and 2 pi, and then make a random vector. But I don't want a random unit vector. I want a random vector whose square, the square of whose length is equal to 2, so that on average the square of each component is equal to 1. Let's check that we've got this right. I'll generate 10,000 of these vectors from a random angle. Notice I'm multiplying by the square root of 2 in order to make the square of the resulting vector equal to 2. And I save the square of the first component, the square of the second component, the product of the 2 components, and when I'm done, I take the average of the 10,000 values. And if you look, you see the average of the squares is very, very close to 1. The average of the products is very, very close to 0. Now we can try this idea, but instead of looking at squared components, what we will do is take the dot product of df acting on h with h itself. If this is positive, it means the vector field is pointing out. Negative means it's pointing in. and here is the mean of our outness. It came out to 7.06. Let's look at df, and in particular, let's look at its trace. The trace is 7. And that, in fact, is the general rule for divergence. The divergence of a vector field is the sum of the diagonal entries in its Jacobian matrix. Now let's try the same thing with our counterclockwise idea. You may recall that if you apply a 2 by 2 matrix to a vector, and the result is counterclockwise relative to the original vector, the determinant of the matrix that you get from df acting on h is the first column, h of the second column is positive. If, on the other hand, the second is negative, is clockwise with respect to the first, we get something that's negative. So we can use this idea on a single vector. Make a matrix whose first column is our increment h, whose second column is our result df acting on h, and in this case it turned out to be positive. But one vector doesn't prove anything. We again have to average over all directions. So I will do this using exactly the same code 10,000 times. The only change is that what I'm doing now is calculating the determinant of the matrix whose first column is the increment h, whose second column is df acting on h. And when I average that up, I get something that's very close to 3. If I look at df, I discover that the difference between the off-diagonal entries, lower left minus upper right, is equal to 3. This quantity is called the curl of the vector field. It results from the difference of the off-diagonal entries in the derivative matrix. Positive means the field circles around counterclockwise. Negative means it circles around clockwise. Here's a famous example from physics to which I'll apply exactly the same technique. This vector field is the one you get if you have a long, thin line of positive charge extending along the z-axis. Its magnitude is 1 over r, and it points straight out. And without reading through the code, I will just repeat the same plots. There's what the vector field looks like, and you look at it and you say, well, it doesn't appear to circle round either way, but I can't really tell whether it's going out on the average or not. Indeed not. You have to look at the derivative. So let's do the same thing with the Jacobian. And now it's quite obvious what's going on. Along 2 of the diagonal directions, in the northeast and southwest quadrants, it's coming in. For the other 2 quadrants, it's going out. On average, it's neither out nor in. It also, in some places, swirls around one way. In other places, swirls around the other way. It doesn't appear to be either clockwise or counterclockwise. And we can check that by computation as well. We repeat the computation of the divergence, averaging over 10,000 random vectors. The average is very close to 0. We form the determinant of the matrix whose left column is h, whose right column is df acting on h. Take the average of that. It's all close to 0. And if you look at the derivative matrix, you'll see that its trace is 0, and the difference between the off-diagonal entries is also 0. This is a field with no divergence, no curl, which is characteristic of an electric field in space where there is no electric charge. An easy way to make a vector field is to start with a scalar field, just a function of x and y, and compute the gradient. I have computed the gradient by rules of ordinary calculus and just written down the formulas. You can check it for yourself if you like. I also need the vector version of exactly the same function, and I will plot it in exactly the same way. There are some contour lines, and here are the arrows. And as you would have expected, the arrows are perpendicular to the contour lines. That's because the gradient always points perpendicular to the contour lines along the direction of greatest increase. So that's our vector field, but we want to look at its derivative. So we take the Jacobian matrix, round it off, and we get some weird mess. But we can plot it. And once we plot it, it's apparent to the eye that it's neither clockwise nor counterclockwise. That's in fact a characteristic of vector fields that arise as gradients. As you can easily confirm by direct computation, the curl of a gradient is always zero. Not necessarily the case with the divergence. We'll calculate the divergence by our standard averaging technique. The mean outness is 22.15. The trace is 22.16. This is a field that has a positive divergence, basically because where it goes out, the vectors are much longer than where it's coming in. Now, how do we extend this to 3 dimensions? The tricky part is to generate a random increment vector that is equally likely to point in any direction, and we want to make sure that the average value of the square of each component is equal to 1. If the vector points equally likely in all directions, we'd expect if we took the product of 2 components, that would be positive half the time, negative half the time, and average out to 0. So we'll make all values of z equally likely. We will make all longitudes equally likely. And we will then check if we generate such a vector that the squares and products have the desired quantity. Generate a z component, generate a random angle, use 1 minus z squared as the square of the radius of the circle that will give us x and y, and multiply by the square root of 3 in order to get each of the 3 components to have an average square equal to 1. Let's see if it works. When we average the squares, the result is very close to 1. When we average the products, the result is very close to 0. We can't plot this field on a flat computer screen, but we can still do average outness exactly the same way. So let's create a vector field in R3 with some rather arbitrary functions and calculate the derivative where x, y, and z are all equal to 2. This gives us a 3 by 3 Jacobian matrix. And what you'll probably find interesting, especially if you're a physicist, is that these 9 numbers get converted in physics to just one vector and one scalar. The vector is the curl, the number is the divergence. So you're basically trading in 9 numbers for just 4 that are of physical significance. Let's do our standard outness calculation the same way we did our test, except this time the quantity whose average we will compute is df acting on h times h, the dot product. And when we do that, the mean outness and the trace, the divergence, are both very close to 6.5. In 3 dimensions is an equally clever way of defining the cross product. Here's our old cross product function. If we apply it to one vector, then we can take the cross product of df acting on h with h, and the average of this quantity is what physicists call the curl. I'm going to do this very many times. With a little patience, I can do it 100,000 times. So I generate my random vector. I save the vector that should be the curl. I wait till the red light goes off, which means I've done my 100,000 calculations, and then I apply the mean function to average the results, and look at what we get. If I take df2, 3, that's row 2, column 3 and subtract off df3, 2, I get 1.5, which was very, very close to the first component of the average value of df acting on h times h. So we have found a way to define the curl as an average.